Hello, and welcome to our session on CMOS implementations of digital logic circuits. As a review, let's take a look at the basic CMOS building blocks, NMOS and PMOS transistors. In the digital world, transistors are modeled either as open switches or closed switches. An open switch is modeled as an open circuit, and a closed switch is modeled as a short circuit. For an NMOS transistor, which serves as an active pull-down device, when the input to the transistor is equal to a high or a 1 value, then the transistor is modeled as a closed switch or as a short circuit, as shown here in the middle diagram. In contrast, when the input is a low or a 0 value in digital language, then the transistor is modeled as an open circuit, as shown as the diagram on the diagram in the far right. In contrast, a PMOS transistor, the other half of CMOS, operates exactly the opposite to NMOS. When the input to a PMOS transistor is low, the transistor is modeled as a switch closed or short circuit. In contrast, when the input to a PMOS transistor is equal to a high, or 1 value, the transistor is modeled as an open circuit, or an open switch. In this way, we can model NMOS and PMOS transistors in digital logic circuits and implement them using CMOS. Let's take a look at a few examples to understand how this works. In this first example, we have two inputs, N1 and N2, and each input is going into two transistors, one NMOS transistor and one PMOS transistor. The two PMOS transistors, P1 and P2, when they see an input of 0, turn into short circuits as discussed in the models of the previous slide. So here we'll have a short circuit for P1, a short circuit for P2. In contrast, when the inputs 0 and 0 go into the NMOS transistors labeled N1 and N2, then we model the resulting transistor as an open circuit. And in this situation, when we put the models in for the transistors, two open circuits for the transistors N1 and N2, and two short circuits for the transistors P1 and P2, out is now directly connected to VDD, which gives us a digital 1 at the output for the input combination of N1 equal to 0 and N2 equal to 0. We can continue in the truth table by looking at the next combination when N1 and N2 are 0 and 1 respectively. An input of 0 to a PMOS transistor P1 results in that transistor acting like a short circuit, and when N2 is equal to 1 into P2, the resulting transistor is modeled as an open circuit. On the bottom half of the circuit, when we put an input of 0 into N1, it acts as an open circuit, and when we put an input of 1 into N2, it'll act as a short circuit. So now if we go ahead and replace the transistor with these models that we've determined in the truth table, what we find here is that, again, out is short-circuited to VDD. And in that situation, VDD represents a digital 1, so once again we get a 1 at the output of this transistor circuit. N1 and 2 equal to 1 and 0 respectively gives us exactly the opposite situation, with P1 now an open, P2 a short, N1 now a short, and N2 now an open. This results in a very similar model to the previous slide, with N1 modeled as a short, N2 modeled as an open, P1 modeled as an open circuit, and P2 modeled as a short circuit. We get out directly connected to VDD, which again gives us a value of 1 at the output. In the last combination in the truth table, N1 and N2 are both equal to 1, which means both of the PMOS transistors will be equal to open circuits, and both of the NMOS transistors will act as short circuits. When that happens, what we find is a direct short between output and ground, which gives us a 0, and two open circuits allow no connection between the output and VDD, so the output is therefore a 0. And we can see now from the truth table that what we've just implemented here is the familiar two-input NAND gate using 4 transistors, 2 PMOS and 2 NMOS transistors. Looking at yet another logic gate implemented in CMOS, we can follow the same analysis to figure out what does this particular circuit do. When N1 and N2 are both equal to 0, the PMOS transistors both turn on and are modeled as short circuits, and the 2 NMOS transistors act as open circuits. When we go ahead and put that model into the circuit, P1 is a short, P2 is a short, and both N1 and N2 act as open circuits. What we see here is a direct connection between the output and VDD, and the output goes to a value of voltage equal to the power supply, or VDD, giving a digital 1 at the output. Continuing with the analysis now with N1 equal to 0 and N2 equal to 1, let's take a look at what happens. N1 into the transistor P1 gives us a short circuit. N2, a value 1 into the transistor P2 gives us an open circuit. And N1 into transistor N1 gives us an open circuit because the input is 0. And finally, N2 into an NMOS transistor at N2 gives us a short circuit. So what we have here now, N2 models as a short, N1 is an open, P1 is a short, and P2 is an open circuit. And now we see a direct connection to 0 between the output and 0, giving us a digital 0 at the output. Moving on to the next combination, when N1 is equal to 1, that means the transistor P1 will be an open circuit, and the transistor N1 will be a short circuit. When N2 is equal to 0, P2, on the other hand, will be a short circuit, and N2 will become an open circuit. Putting these models into the transistor circuit, P1 is an open circuit, P2 is a short circuit, N1 is a short circuit, and N2 is an open circuit. We can see here that we have a direct connection again to 0, giving us an output that's also a digital logic 0. And in the last line in the truth table, when N1 and N2 are both 1, both of the PMOS transistors turn off or become open circuits. N1 and N2 both turn on or turn into short circuits. And we can see now that we have 2 parallel shorts connected to 0, while the transistors P1 and P2 both act as open circuits and provide no connection to the output, leaving us an output of 0 once again. So now that we've completed the truth table, we can see that this truth table represents the familiar NOR gate, and that's how we implement a NOR gate with 2 PMOS and 2 NMOS transistors, configured differently than the 2-input NAND gate, but still providing a valid digital logic function. Let's take look at one more example here. Here's an 8-transistor CMOS circuit, and let's see what kind of function we get out of this circuit. So we do the same thing that we've done on previous slides, go through each transistor one by one to see if it's modeled as a short circuit or an open circuit. Here at P1, the input 1 is 0, but into P1 is the inverse of input 1, or 1. In 2 is equal to a 0, so into P3 we have the opposite of that, or 1. N1 going into P2 is equal to a 0. N2 into P4 is also a 0. N1 not on the bottom half of the circuit here gives us a 1 into an NMOS transistor. N2 not is equal to 1. N1 is equal to 0. N2 is equal to 0. And when we look at this, we find that we have a direct path from the output to ground, so the output goes to a 0. And that is because the transistors N1 and N3 are both acting as short circuits, while the transistors N2 and N4 are acting as opens. The transistor P1 is acting as an open circuit, P2 is acting as a short circuit, P3 is acting as an open circuit, and P4 is acting as a short circuit. So that gives us the first line of our truth table. We can do something similar for the remaining two lines. In the next example, N1 is equal to 0 again, which gives us a 1 here at N1 not, a 0 here at the transistor P2, a 1 here at the transistor N1, and a 0 here at the transistor N2. N2, in contrast, is equal to 1, so that'll give us 0 here at the input to P3, and a 1 into the transistor P4. N2 not going into N3 will be 0, and N2 going into N4 will be 1. Now we can see here that there's no pathway to ground through the NMOS configuration because there's an open circuit in the way during every possible pathway from out to ground. However, there is a pathway directly to VDD through P1 and P4, so our output in this case is equal to a 1. We can do a similar examination in the third row of the truth table when N1 is equal to 1 and N2 is equal to 0. Let's take a look what happens there. N1 not is equal to 0, N1 is equal to 1, N2 not is equal to 1, and N2 is equal to 0. Now right away we can see we have the opposite situation we did in the previous slide, but there's still a direct pathway to VDD, which will give us an output of 1. And finally, we can look at the fourth line of the truth table when N1 and N2 are both equal to 1. And right away we can see there's a direct pathway from the output to ground, which will give us an output of 0 in the last line of the truth table. And that completes our truth table, and what we have here is the familiar XOR gate as the function that's being implemented by this 8-transistor circuit. Now, not all logic gate implementations work well, and it is possible for designers to make mistakes. So let's see what happens here with this particular implementation on this last example. We've already filled in here the models for the 4 transistors, P1, P2, N1, and N2. So let's take a look at what happens in each case. In the first line of the truth table, P1 and P2 are both equal to short circuits, so there's a direct connection from out to VDD and no connection from out down to 0. That logically gives us a 1 at the output of the transistor level circuit. And on the next line, what we find is that P1 is a short, but N2 is also a short, and this gives us a pathway from power to ground. So what we effectively done here is create a power ground short. And there's very little reason to ever create a power ground short because it draws a high volume of current and usually leads to a catastrophic destruction of the device. So this makes this a very bad design. The same thing happens when we have a 1 and 0. We have a short to VDD through P2 and a short to ground or 0 through N1, which gives us again another power ground short. In the last line of the truth table, we have 2 short circuits to ground and none to VDD because both P1 and P2 are acting as open circuits. So here we get a valid 0 at the output. But in general, what we've done here is we've created 2 power ground shorts, which are overall a bad idea, and this is an invalid design for that reason. So in summary, we can implement any of the basic logic gates using CMOS, a combination of NMOS and PMOS, as long as we can connect them in the right configurations to avoid any power ground shorts or a floating or not connected output. The 2 one-input AND gates are both constructed in CMOS using one PMOS and one NMOS device. But the buffer, which is also a one-input logic gate, requires 2 inverters to make, so that doubles the transistor count. An inverter itself only takes 2 transistors, but a buffer, since it requires 2 inverters, will take 4 transistors. And these other logic gates, the 2-input NAND gate, we have 2 PMOS and 2 NMOS transistors for a total of 4 transistors. And it's important to note that the NAND gate is the fastest of the 2-input logic gates, or any n-input logic gates in digital logic. A NOR gate also takes 4 transistors, and with the NOR gate make for the most space efficient of the 2-input logic gates, and likewise for 3 and 4 input gates. An AND gate requires inverting the output of a NAND gate, hence it takes 2 more transistors than a NAND gate and is a little bit slower. And likewise, the OR gate is a NOR gate followed by an inverter, which also makes it slightly slower than the basic NOR gate. XOR and XNOR gates, we've looked at one implementation of an XOR gate, but in general both types of gates are complex logic and require that both inputs be inverted, which increases the total number of transistors if we take into account the inverters that are involved. So in CMOS, we can implement any basic function in CMOS by taking a look at these basic rules. First, we find that AND gates become NMOS series connections, so any AND function in the complex logic F becomes NMOS in series, and any OR function becomes NMOS in parallel, and vice versa for PMOS. So let's take a look at what this looks like. To implement the function F now, an AND function, or NMOS series connection, will be required to implement A and B naught. And for simplicity, we've left out the actual inverter required to produce A naught for now. And the function A and C, A naught and C, also requires a series connection of 2 NMOS transistors to connect A naught and C together. So this produces A naught C, and this leftmost branch produces A naught B. And to construct the PMOS half of this circuit, we're just going to do the opposite. So where A naught and B are in series here, we'll just put them in parallel with the PMOS to implement the right functionality. So A naught and C and the PMOS half of the circuit will be implemented as 2 transistors in parallel, and likewise for A naught and B. All roads through PMOS end up connected to VDD, so we'll show that connection as well. Now what we've produced here is an inverted F, because CMOS is naturally inverting, and in order to go back and get F rather than F naught, we'll have to put the whole function through another CMOS inverter. And once we do that, we'll get the correct implementation for this function F as shown here. So what we've looked at today is CMOS implementations of various types of logic gates. The basic logic gates, inverters and buffers, as well as ANDs, NANDs, ORs, and NORs, as well as XOR, XNOR, and some more complicated complicated Boolean functions. Because of limitations in device physics, the PMOS transistors in a CMOS gate always perform the function of pull up, while NMOS must always pull down or make connections to zero. Well, that's all for CMOS implementations of digital logic gates today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.